Every single day, hundreds of thousands of aircraft perform this incredible, intricate dance across our skies. And behind all of that, there's this one single-minded obsession: efficiency. Just a 1% improvement can save billions of dollars, literally erase mountains of emissions. But here's what most people don't realize. The next huge leap forward in aviation, it might not come from a wild new engine or some radical wing design. Nope, it might come from something so tiny you literally can't even see it. So what is it? What's this invisible wall that every single airplane, from a tiny little prop plane to a giant super jumbo jet, is constantly fighting against? Well, the beautiful irony is that it's the very thing that keeps it in the air in the first place. It's the air. The air itself. Now, engineers have a name for it. They call it drag. But you can just think of it as this constant, powerful friction. It's a force that just wants to grab onto every square inch of a plane's surface, forcing those massive engines to burn just incredible amounts of fuel to keep pushing forward. Honestly, taming this one force, it's the most expensive and the oldest challenge in aviation. It's really the villain of our story today. For decades, the answer was always pretty simple. Just add more power. Bigger engines, more thrust. But we're really starting to hit a wall with that brute force approach. The truly elegant solution, the one that's going to give us the next real breakthrough, isn't about fighting the air harder. It's about being smarter. It's about learning how to just slip through it more gracefully. And whenever engineers are looking for that kind of elegant solution, where do they often look? To the greatest innovator of them all, nature. There's this whole field called biomimicry, where we basically study the blueprints that millions of years of evolution have left for us. And when it comes to moving through a fluid, like air or water, with almost impossible efficiency, there is one predator that is the absolute undisputed champion. The secret? It belongs to the shark. You see, a shark's skin isn't smooth at all. It's this marvel of natural engineering, covered in countless tiny, tooth-like scales that create these microscopic parallel grooves. And these grooves are called riblets. What they do is brilliant. They manage the thin layer of water right next to the skin, keeping the flow really smooth and organized. And that just dramatically cuts down on drag. So the theory became beautifully simple. What if we could wrap an airplane in a kind of synthetic shark skin? Okay, so that sounds amazing, right? A total silver bullet, a simple texture inspired by nature that could completely change how efficient flying is. Which of course leads to the really obvious question. If we've known about this stuff for decades, why isn't every single airplane already covered in these things? Well, the answer comes down to a massive, massive manufacturing problem. So for these little riblets to work their magic, they have to be almost impossibly small. We're talking fractions of a millimeter. And for the longest time, making them with that kind of precision was just painfully slow and incredibly expensive. We're talking about methods like precision milling, which could take weeks just to make one tiny little test sample. Other ways involved complicated chemical etching or casting. The science was totally solid, but actually making the things, well, that was a huge bottleneck, both in time and in money. So here's the real puzzle. It wasn't about proving that riblets worked. We already knew they did. The real grand challenge was figuring out how to make these super intricate, microscopic patterns with near-perfect accuracy. But, and this is the key, to do it fast enough and cheap enough to make it practical for research, let alone putting it on an actual plane. And this is where the story gets really good. The solution didn't come out of some multi-billion-dollar aerospace lab with all these exotic, gleaming machines. No, it came from a pretty humble device, the kind of thing you might find sitting on a desk in a high school classroom or a hobbyist's garage. A couple of researchers, Volkan Korkut and Hurrem Akbiak, turned their attention to one of the most common, most affordable types of 3D printers out there, fused deposition modeling, or FDM. These are the workhorses of the whole maker movement. They're cheap, they're super customizable, they're open source. The big question was, could a machine that was designed to print, plastic toys and trinkets, possibly have the kind of microscopic precision you need for cutting-edge aerospace? Well, it was a huge job of just pure refinement. They basically had to push this consumer-grade tech to its absolute limit and then way beyond. First, they tackled the hardware. They painstakingly calibrated every single physical part, from how far the nozzle was from the print bed to making sure its tiny opening was a perfect circle. And then they dove into the software, just methodically tweaking all the digital settings, getting this obsessive level of control over the flow and the width of every single tiny strand of melted plastic. And the results of all this careful work were, well, they were just staggering. Before they started, the error in the dimensions was almost 12%. that's completely useless for this kind of application. But after all their adjustments, as you can see, they just crushed that error rate, bringing it all the way down to less than 2%. It was a massive leap in precision. But this right here is the number that changes everything. For the most critical dimension, the height of those tiny grooves, they achieved a final error rate of just 0.19%. Just let that sink in for a second. With a cheap desktop 3D printer, they got a level of microscopic accuracy that used to be only possible with multi-million-dollar industrial machines. It's incredible. And that really shows you the true impact of what they discovered. This is so much more than just a clever little printing trick. What we're actually looking at here is a fundamental shift in how aerospace innovation can even happen. Because what this discovery really does is it tears down the huge financial walls that have always surrounded this kind of advanced research. All of a sudden, university labs, small startups, even just brilliant people working on their own can now design, print, and test new aerodynamic surfaces in just a few hours, not months. It basically democratizes the entire field. It unlocks the creativity of thousands of minds to help solve one of aviation's oldest problems. And you don't just have to take my word for it. The researchers themselves said it best. They concluded that their work proved it was feasible to create these precise micro-scale structures using technology that is, and I'm quoting here, widely available, cost-effective, and customizable. They didn't just print a cool texture. They basically forged a new key and handed it to the entire industry. So it really leaves us with this one profound thought. As we look to the future for the next big revolution in flight, maybe we shouldn't be looking for bigger engines or wild futuristic jets. Maybe the next giant leap forward is already here, just hiding in plain sight, in grooves so incredibly small they're completely invisible to the naked eye.
Just take a look around you. I mean, really look. Chances are you are surrounded by concrete. Our cities, our homes, our roads, our entire modern world is basically built with it. It's the most common man-made material on the entire planet. But this foundation of our civilization, well, it has a massive hidden cost. And once you see it, you can't unsee it.
7%. That number, right there, is the slice of all global CO2 emissions that comes from making just one single ingredient, cement. That's the glue that holds our concrete world together. Now, to put that into perspective, if the cement industry were its own country, it would be the third biggest carbon polluter in the world, right behind China and the US. It's a staggering figure.
But here's what most people don't realize. The solution to this enormous man-made problem might not come from a bigger, better factory. This quote really gets to the heart of it. Nature has already cracked this code. It's been binding minerals together for billions of years. The blueprint for a better way to build isn't something we need to invent from scratch. It's something we just need to rediscover.
So, here's the journey we're about to take. First, we're going to dig into concrete's hidden cost. Then, we'll look at nature's ancient blueprint for a little inspiration. After that, we dive into the incredible breakthrough of literally growing bricks from algae, see what this bioconcrete can really do, and finally, imagine what it means to build our future biologically. All right, let's start with the problem. Why is the one material we rely on more than any other also so incredibly damaging? It's time to meet the invisible giant of global emissions.
So the main culprit here has a name, Portland cement. Think of it as the essential binder. It's the glue for pretty much all concrete, mortar, and stucco. You just can't make modern concrete without it. And here's the catch. The way we make this stuff is an unbelievably carbon-heavy process.
It all starts with digging limestone out of the earth. Then that rock is thrown into a massive kiln and superheated to a mind-boggling 1,450 degrees Celsius. This insane heating process is called calcination, and it forces a chemical reaction that releases just enormous amounts of carbon dioxide that have been locked away inside that rock for millions of years. This one step, this single chemical reaction, is the core of the entire problem.
So that's the industrial way. Brute force and a whole lot of heat. But what if there's a smarter way, a more elegant way? For that, let's turn to nature and take a lesson from some of the planet's oldest and most successful builders, coral reefs.
You know, corals are basically nature's master masons. They take the most common materials imaginable, sunlight, seawater, and even the CO2 dissolved in it, and they use them to build these vast, incredibly strong, and beautiful structures. They're doing complex chemistry without any kilns, without any fossil fuels, just biology.
And this is where it all clicks. This is the question that changes everything.
What if we could copy that process? What if we could learn to build our cities not by burning rock in a furnace, but by growing our building materials just like a coral builds a reef?
That very question leads us directly to a jaw-dropping scientific breakthrough, one pioneered by a team of brilliant researchers and, believe it or not, one of the tiniest organisms on Earth.
This incredible work is coming right out of the University of Colorado Boulder, and it's being turned into a real-world product by a startup called Prometheus Materials. Their core idea is nothing short of revolutionary. They're using microscopic algae to literally grow a biological substitute for cement.
So how in the world does it work? Well, in simple terms, they grow these tiny microalgae in big tanks, bioreactors, and they feed them the same stuff a coral loves: light, water, and CO2. And through the simple, elegant process of photosynthesis, these algae create a substance that works just like cement, binding other minerals together into a solid block.
And when you put the two processes side by side, wow, the difference is just night and day. On one side, you've got traditional cement. The ingredients are quarried rock and fossil fuels. The byproduct is a mountain of CO2. On the other side, biocement. The ingredients are algae, sunlight, water, and CO2. And the main byproduct? Clean, pure oxygen. This isn't just a small improvement, it's a complete rewrite of the entire chemical equation. Okay, it all sounds amazing, almost too good to be true. But this is where the science has to hit the pavement, literally. Does this stuff actually work? Let's look at the real promise of bioconcrete when it comes to strength, scale, and what sustainability really means.
The numbers are seriously impressive. These bioblocks can handle a compressive strength of around 2,000 psi. Now that's strong enough for all kinds of structural uses, like the walls in a house. But the real showstopper is the embodied carbon. That's all the CO2 released to make it. Right now, this process creates 90% less. And the end goal? It isn't just to be carbon neutral. The goal is to be carbon negative.
And this is the holy grail. We're not just talking about doing less harm, we're talking about creating building materials that are actually carbon sinks. I mean, just imagine a skyscraper that has actively removed carbon dioxide from the atmosphere, locking it away forever inside its own walls. Our buildings could go from being a huge part of the problem to a key part of the solution. And listen, this isn't just a cool lab experiment. This is serious business. The market for low-carbon cement is already worth about $2 billion, and it's projected to quadruple to $8 billion in the next decade. Big-time investors, even companies like Microsoft, are pouring money into this technology. That tells you they see a very real, scalable future here.
So let's zoom out for a second. What does all of this really mean for the future? We are literally looking at the dawn of a completely new age of construction, one that works with biology instead of fighting against it.
This whole idea is part of a brand new field, something called construction biotechnology. It's this amazing intersection where material science, engineering, and biology all meet to completely rethink the way we build everything, right from the ground up. Now, of course, it's not going to be easy. There are huge hurdles to overcome. Scaling up production to meet the insane global demand for concrete is a monumental challenge, and the cost has to come down. It has to be competitive with the old stuff so you don't have that green premium that makes sustainable choices too expensive. And of course, the entire supply chain needs to be built out for this to go global.
But these are challenges worth solving, because we started this journey in a world built with a material that pollutes our atmosphere. This technology shows us a future where that's no longer a given. It leaves us with this one, final, powerful thought. What if our cities, the greatest symbols of human achievement, could do more than just stop harming the planet? What if they could actually start to heal it?
Thanks for watching. Support BioVellum by liking, subscribing, and sharing. Let's explore the secrets of nature together.